Now we'll see about magnetic materials. So based on electron theory, magnetic materials are divided into three types, that is diamagnetic substance, paramagnetic substance and ferromagnetic substance. What is this electron theory? And you see electrons are revolved in orbits around the nucleus and they have one rotational motion, and electron also spinning itself. We know plus half and minus half spins is there, and because of spinning of electron and the rotating electron in the orbit, a current is set in the orbit, or a current is set here due to spinning of electron. We know according to Einstein experiment, a current carrying conductor can create magnetic field around it. Suppose if this is the current carrying conductor, and it can create a magnetic field around it. Similarly, here also electrons are revolving in the orbit, that create magnetic field, and the spinning of electron also create magnetic field. But when compared to spinning of electron, and current is very high value, because radius is very small, fast revolution, here slow revolution, and because of that the magnetic field what we get due to spinning of electron in rotating of electron in orbit is less when compared to spinning of electron. So in this case here electron theory is mainly based on spinning of electron, not electron rotation in the orbit. So here we have three different types based on this magnetic field, that is because of spinning of electron we get some magnetic field, and based on this concept we have three different materials: diamagnetic material, para and ferromagnetic material. First we'll see about diamagnetism. What is diamagnetism? So diamagnetism means, so you see there in diamagnetic materials outermost we have paired electrons. One has a positive half spin, means other has a negative half spin. Because of that what you get and a magnetic movement is created like this. Suppose for example you see electron is spinning like this, we get magnetic movement like this. This is a magnetic movement of very small magnetic movement. This is a magnetic movement due to an electron, or magnetic movement due to an atom. So this you simply call atomic magnet, this small one, atomic magnet. And in this case what happen in diamagnetic material, and two electrons are there, always paired electrons are there in the diamagnetic material. Because of that what happen, one has a spin clockwise, means other has anti-clockwise. That's why the net magnetic field created, or net magnetic movement created by these two electrons cancel each other and you get zero. So no magnetic movement we are getting here. Suppose if this diamagnetic atom, if you place in a magnetic field, external magnetic field is there, here a magnetic field is they didn't place any magnetic field here, and here if they introduce a magnetic field which is in this direction, then what happened, one of the electron which is creating magnetic movement opposite to field speed up, and other electron which is creating field in the same direction as magnetic field, that slows down, and the movement of this is reduces, movement of this increases. That means the field which is opposite to external field, that field increases in the diamagnetic material. Due to this what happen, it slightly repel the magnetic field. Suppose example you can take copper. If you bring a copper bar near to a freely suspended magnet and slightly feebly repelled, very lightly, we can't feel that. But if you take a copper sphere on a smooth horizontal table, and if you bring a magnet near to that, it rolls away from the magnet. That is the diamagnetic nature. What is diamagnetic nature? If you are not applying any field, it won't show any magnetic nature, because pair of electrons cancel that both magnetic movement, and net magnetic movement become zero here, and net field also zero. Suppose if you apply external magnetic field, what happen? One of the electron faster, other electron becomes slows down, and because of that one movement increases, other movement decreases. Which movement increases means which is opposite to external field, that increases. Because of that a repulsion takes place. So diamagnetic substance, because of this reason, diamagnetic substances are feebly repelled. Feebly means very small amount repel in strong magnets. That too we can observe if you bring a strong magnet near to the copper, then we feel that repulsion here. Okay. And other example for diamagnetic materials are superconductors. All the metals which are good conductors, those are cooled to very low temperature, that is minus 160 degrees centigrade, very low temperature, means 30 Kelvin, 40 Kelvin, like that. Then they are converted into superconductors. That means they didn't offer any resistance, current easily flow through them. Those are called superconductors. And superconductors at low temperature behaves like a perfect diamagnetic material. Because of that, what happened? It repels the magnet. So that's why while arranging that fastest high speed running trains, that is superconductor trains, they use this concept at low temperature, magnetically levitated. That means they arrange a magnet at the bottom, and above that the train is like this, and because of repulsion, what happened? Repulsion, it will be float on the ground like this. It will be float. The levitation of superconductor is because of due to their diamagnetic nature, that is repelled by the magnetic nature. If you see a diamagnetic metal rod, if you can suspend any manner. Suppose you can take diamagnetic rod is like this or like this, any position, and if you suspend freely with a thread, and it will be stand perpendicular to the Earth's magnetic field. Or suppose if BH is there, like this, BH is in the direction, you can release this metal rod, this copper rod, nothing but diamagnetic rod only, and if you suspend at any position, finally it stops perpendicular to field direction. Perpendicular to field direction stops. Suppose other materials, what happen? Suppose if it is a magnet, it align with the magnetic field, no, but it stands perpendicular to magnetic field. That is a nature of diamagnetic rod. We can identify whether this material is a diamagnetic or not means if we suspend this bar magnet, this material rod, and free in external field, then if it stands perpendicular to the field, we can say that is diamagnetic rod. Copper. Suppose a normal uniform magnetic field. Uniform magnetic field means all lines are parallel and equidistant. If you are introducing a diamagnetic substance inside the field, the lines are moving away. They are diverging here and they move away from the material. So less number of magnetic lines are passing through that. Initially, suppose for example, here initially some X number is there. Now we get less than X number. So field lines are diverges. They are not passing through copper bar here. Copper nothing but diamagnetic material. That is the nature of diamagnetic material. Suppose if you are applying magnetic field on diamagnetic nature, it shows a slightly repulsive force. Suppose if you remove that field, immediately it behaves like a non-magnetic material. That is immediate. That means suppose if you remove within fraction of seconds, as soon as the magnetic field also disappear inside the diamagnetic material. And here, if you think about relative permeability, mu R value is less than 1. Very small value it have, relative permeability is less than 1 we get. And what is magnetic susceptibility? We have relation susceptibility 1 plus susceptibility is equal to mu R now. So if it is less than 1, send this one that side, less than 1 minus 1, what do you get? Negative value. That only magnetic susceptibility of diamagnetic substance are smaller and having its value negative. Psi is less than 0 we get. And you see here magnetic susceptibility or magnetism of diamagnetic material is not depend upon temperature, or increasing temperature, decreasing temperature, and the susceptibility or magnetic nature of the diamagnetic material is not affected. Suppose you can see here a small graph I draw here, and temperature increases, diamagnetic nature, that is susceptibility, is constant. It is not changing, not depend upon that. Suppose if you want to check other property of diamagnetic, so take diamagnetic liquid, like diamagnetic liquid means, so you can take mercury is one of the example for diamagnetic. liquid. And mercury, suppose if you take a watch glass means that is like a bowl only, glass bowl like. If you are using a metal bowl, what happen? That magnetic nature is interfere with this. That's why they use a glass plate. That what we call watch glass plate, watch glass. And inverted watch glass, they poured with a diamagnetic liquid. And if you bring two poles near to that, then what happen? Because of repulsion, this liquid is try to move like this and it is accumulated here. Suppose if you bring these magnetic poles very nearer and to move away, there is no chance to pile here, and they are splitting like this. They are moving away from the poles. So here also they are trying to move away from the poles. That's why they come closer. If you bring these magnetic poles very close, they are moving like this away from the poles. So from this we can say this diamagnetic material is slightly repelled by the magnetic field. Suppose another point is there, when it is kept in non-uniform field. Suppose if you take a copper ball is placed in a magnetic field like this. Then what happen? Here you see, here lines are far away, here lines are closer, here high field is there, here low field is there. So diamagnetic materials are moving from high field region to low field region because they are trying to move out of the field. So that is the reason they are moving from high field region to low field region. And example for diamagnetic materials is copper and Az, H2O, Au, Sp, bismuth and mercury. Now only diamond also. So different examples is there, and you see this is about diamagnetic materials. Main important points of diamagnetic materials. First of all, they have paired electrons, so net magnetic movement become zero. And if you place external magnetic field, the light field is created in opposite direction. Due to that, they repel each other. And other properties, susceptibility, relative permeability, and how it depends upon temperature. Different cases, if you suspend a metal rod, that diamagnetic rod, what happen? And if you play a copper ball, what happen? These all cases also important here. And other type of material, that is second type of material, is paramagnetic material. What is paramagnetic material means? There in diamagnetic material always electrons are exist in pairs. That's why net magnetic movement become zero. But here electrons in outermost orbit or alone single electrons are there. They have some resultant magnetic movements. Suppose one of the electron is spinning like this, it get a magnetic movement like this. This what we call atomic magnet. So like this and like this. So each and every atom, suppose maybe in outermost orbit of atom, only one electron is there. One atom behave like one magnet, one small magnet. That's why they call atomic magnets. But initially what happened? These atomic magnets is, suppose if you take some amount of substance if you take, and these atomic magnets are randomly arranged, not in a same direction. Due to this, what happened? One of the magnet will be cancelled by other, and these all are net magnetic field is cancelled, and finally net field become zero. If you are not applying any external field, and field created inside also, resultant magnetic movement also zero here. B net is equal to 0 we get, because all are randomly arranged. So some are upward, some are downward, left, right, like that they are arranged. So B net is equal to 0. What happens if you place this paramagnetic material inside a magnetic field? These all atomic magnets are aligned in the particular direction, which is same direction as external field. So because of that, what happened? Inside also additional magnetism is possible. Suppose externally outside applied is H, you can think inside what it induce I. That what we discussed in earlier class. Suppose H is the applied field and I is the induced field. In case of diamagnetic material, what happen? This induced field create opposite to external field. But in paramagnetic material, what happen? It create in the same direction. Suppose if you remove this magnetic field outside, again these are disturbed and they are converted into again random nature. Because of the temperature of the body, what happen? These atoms are vibrating. Because of vibration, they lose their alignment nature. So in absence of external magnetic field, then they are randomly arranged. If you send a magnetic field through that. They arrange properly, they align properly, and it create extra magnetic field. So in this case, what happened due to this? These materials are feebly attracted, slightly attracted here. Suppose if you suspend this type of rods in magnetic field, they stand in the direction of the magnetic field. Their diamagnetic material perpendicular, here parallel. There in diamagnetic material, what happen? And a substance, suppose a smooth sphere, if you release on the table, and it moves from high field region to low field region. There in diamagnetic material, what happen? It moves from high field to low field, here low to high. These are moving from weaker strength to stronger strength. Here what happen? In uniform magnetic field, if you are introducing a paramagnetic substance. If you are introducing paramagnetic substance, means what happen? The flux lines which are going outside also divert their direction and they are passing through this material. Means the lines which are magnetic lines of force passing through that increases. Because induced field and applied field H and I both are in same direction created. In diamagnetic material, what happen? They are created in opposite direction. That's why flux lines are going away from the material. Now, most of the lines are passing through the material. Due to that, magnetic nature increases here. And relative permeability is greater than 1. It's more than 1. Relative permeability greater than 1. Magnetic nature, it shows very good magnetic nature, it shows. Suppose if you remove the external field, and here you see, if you apply the field and they are aligned each other, if you remove the magnetic field, external magnetic field, what happen? Again they disturb and they arrange randomly because of its temperature. So if you remove the magnetic field, what happen? They lose magnetic nature. In diamagnetic nature also same only. And now you see, and it loses magnetic nature if you remove the magnetic field. And magnetic susceptibility of paramagnetic substance is positive, little greater than 0. So paramagnetic substance is greater than 0. They are negative diamagnetic material. Here greater than 0 means positive value. Mu r is there less than 1, here more than 1. In this case it is greater than 0 we get. And you see the liquid case, here you see, and if you take a paramagnetic liquid in a watch glass and if you bring the magnetic poles nearer to that, then what happens? Total magnetic liquid is and filed here and it will be rise at the center. Because magnetic field is at the center, here at this point is more. So all the material comes to that point. Accumulation takes place. And how paramagnetic material depend upon temperature. And already we discussed diamagnetic material is not depend upon, that nature is not depend upon temperature. But here paramagnetic material nature is inversely proportional to temperature. Susceptibility is inversely proportional to temperature. Already we discussed, because of temperature what happen? Alignment of atomic magnets are disturbed. So they lose their magnetic nature. That means susceptibility or magnetic nature of the paramagnetic material is inversely proportional to temperature. So psi is equal to some constant C by T. If we draw the graph for this, how susceptibility or induced field inside created means psi and T graph rectangular hyperbola we get because inversely proportional. And here about diamagnetic material. What is diamagnetic material nature? These are having single electrons in the outermost orbit. Because of that you get atomic magnets, and these are randomly arranged first. If you apply external field, they are properly arranged themselves. If you suspend a rod of paramagnetic material in the field, that is stands in the direction of the field, and if you place a metal rod inside the magnetic field, that most of the flux lines are going through that, and relative permeability greater than 1 and the susceptibility greater than 0, and liquid if you place the piles at the center, and inversely susceptibility is inversely proportional to temperature. And graph nature, that is about paramagnetic material. Now about ferromagnetism or ferromagnetic materials. So ferromagnetic materials contains inside domains. What are domains means? Domains are contain same atomic magnets only, but in paramagnetic material what happen? Atomic magnets are randomly arranged. But in ferromagnetic material, and these atomic magnets are arranged in proper order up to some region. In other region, all are in other order. So in a particular region, all the atomic magnets are in same direction. Alignment is there. Here I divide into 4 regions, and here magnetic moment is horizontal, here slantwise, here slantwise, here vertically upward, like that is there. These regions, what you call, that means where this atomic magnets all are aligned in the same direction, the total region what we call domain. So in ferromagnetic substance what happen? For every this much volume of 10 power minus 6 to minus 2 centimeter cube, this much volume of the material, that is ferromagnetic material, contains 10 power 7 to 10 power 21 atoms we get in that. Each atom behave like a bar magnet. Bar magnet means atomic magnet. So those are a group of atomic magnets are aligned like this in the regions. These regions what we call domains. Suppose if you are not applying any field externally, these domains remains like that only. Net field is 0. Reason, some of the domains shows horizontally, some are vertically upward, and some are inclined. So net field due to this is 0 we get. But what happen if you apply external field? Suppose if you apply external field, the domains which are same direction as external field, you see external field is like this, and the domain which is in the same direction, this is the first domain which is in the same direction, that expands, that increases, that range increases. And other domains also present, the direction and the bottom here is upward, that sinks, that domain sinks. So most of the area of this material occupied by this domain, and which is in the direction of external magnetic field. This is the reason it shows a strong magnetic attraction. This ferromagnetic substance, example steel, iron, this nickel are example for this. These are showing a strong magnetic nature. Ferromagnetic substances are strongly attracted by the magnet. If we suspend this material in the magnetic field, then definitely they stand in the direction of the field like a paramagnetic material only. But reaction is fast here. And when compared to here also, if you place a small sphere and if you release a small ferromagnetic sphere inside the field, and that moves from weaker field strength, weaker to stronger region. Same as paramagnetic material only. Here also, if you place a